Okay, another really important lesson today. I want to break it in two parts. The first part's going to be all conceptual, second part all calculations. So, first off, do this question. Wow, great job using the formulas that we learned in the last two lessons to solve that problem. Okay, so today we're going to discuss the idea of a Gedanken experiment. Gedanken is German for thought, Thought, not some other weird spelling. Gedanken experiments. This means an experiment. You don't actually do the experiments. You just kind of think about it in your head. And you can actually learn a lot from Gedanken experiments without actually doing anything physically in a lab. So here's the Gedanken experiments. It answers this really important physics question. What falls faster, heavy objects or light objects? Let's say I have a 3 kilogram rock, a 2 kilogram rock, and a 1 kilogram rock. Some of you guys might know the answer, but let's say you just walk up to a random person on the street and ask them, hey, what will hit the ground first if I drop them all from the same height? A 3 kilogram rock, 2 kilograms, or 1 kilogram? They're going to say one of two things. They're going to say either 3 kilogram or they'll all hit the ground at the same time. We can answer this question without actually doing it. You're ignoring air resistance, you're dropping them all from the same height at the same time to the same ground below. Which one hits the ground at the same time? Here's how we do this idea. Assume the 3 kilogram rock is the fastest, then the 2, then the 1. Some of you guys probably already said that. Some of you guys might disagree, but this is a very common idea held by a lot of people. People say, oh, the 3 kilogram rock will hit the ground first, then the 2, then the 1. Heavier objects are pulled more by Earth's gravity, so they fall faster. And that reasoning makes sense to them. So, say this. What if you instead took the 1 kilogram rock and tied it to the 2 kilogram rock? This is so easy, even a baby could tell me. Hey Sage, if I tie a 2 kilogram rock to a 1 kilogram rock, how heavy is that bundle of rocks? 3 kilograms. Yeah, that's right. So, these two rocks together should fall faster than they did when they were separated. Okay, fine. That still follows along with my reasoning that heavier objects fall faster than lighter objects. But let's say while they're falling, they get separated. Now, which one will fall faster? While they're falling, the ropes come undone, and instead they separate into 2 kilograms and 1 kilogram again. Well, under the old reasoning, the 2 kilogram rock will fall faster, and the 1 kilogram rock will now fall slower. This makes no sense. We've reached a contradiction. When they were tied together, they both fell faster. But if the rope comes undone and they separate, according to our reasoning, the 2 kilogram rock will start to fall and the 1 kilogram rock will kind of fall slower. So eventually, the 2 kilogram rock will be below the 1 kilogram rock. So, if the 2 kilogram rock falls faster when it's separated, that means the 1 kilogram rock was slowing it down. That means being tied to a 1 kilogram rock makes a 2 kilogram rock slow down. But that doesn't make any sense because we just said when you tie them together, they actually speed up. So which is it, speed up or slow down? Neither one, Mr. Lamb. Wow, good job, Daisy, yeah. When you tie two rocks together, They don't speed up or slow down. 1 kilogram rock will fall the same speed as 2 kilogram rock, will fall the same speed as them tied together. Or if they fall apart, they'll still fall the same speed. All masses, if you ignore air resistance, that's a really important idea. If you ignore air resistance, they all fall at the same speed. I wasn't going to show this video, but it's like a classic, so let's just watch this. In real life, we don't see this because if you drop like paper has massive air resistance. But if you were to go to a place without air resistance, like the moon, you would see this very famous experiment.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct.
You can't really see the feather.
Findings. Two of them here, and hopefully they'll hit the ground at the same time. How about that?
That little flash of white, that's a feather.
How about that?
They did fall at the same speed.
It proves that Mr. Galileo was
At
correct.
the same time. So it does work. You can try it. Grab a small rock and a big rock, as long as they're not too like papery, light, fabric-y kind of stuff. As long as they're both, like I was talking about with the pendulums, dense, solid objects. If you drop them from the same height at the same time, they'll hit the ground together. You can very easily prove this with actual objects, but a Gedanken experiment will help you prove it without even doing the experiments. And we'll talk about a few of them in the future. It's okay if it doesn't really super make sense, but hopefully it makes some sense. So I said a lot of times that objects fall the same speed. I was lying. That was not true. They don't all fall the same speed. Here's another thought. This is not really a thought experiment, but here's just a thinking activity. Let's say you go down to the Empire State Building on 34th Street, 5th Avenue. You pass by, and there's lots of these guys in red hats trying to give you a tour, and you don't want that. Let's say you're taking a nice walk past the Empire State Building, and people are on top, and they're throwing pennies off the Empire State Building. Sounds pretty scary. There's an urban legend that if you get hit in the head by a penny thrown off the Empire State Building, you will die. Not a very interesting myth, but sounds reasonable to me. I don't know. Would you guys want to go try it? What do you think? Would you rather? I don't have a penny. Be right back. Okay, so here I have 2 pennies. Would I rather be hit in the head by a penny dropped from a foot above my head? Or would I rather be hit in the head by a penny dropped from all the way on top of the Empire State Building? Of course, I'd rather be hit in the head by a penny dropped from a foot above my head. Isn't that right, Hazel? Yeah, of course. Why? Why, Hazel? Why? Because the penny that fell really far is going to hurt more. That's true, but that's not really good reasoning. Why not? Your skull... Okay, listen up, Hazel. Your skull doesn't know how far the penny came from. The penny could have come from outer space. That's not really what affects your head and your skull and your brain. What about the penny actually matters when it hits your head? I'm going to ask this kind of question a lot. What is important when your head gets hit by a penny? And whenever I ask these questions, the answer is always a physics term we've talked about. Distance, velocity, speed, displacement, acceleration is one of those. So I lost all my markers. What's different about a penny that falls from way on top of Empire State Building versus a penny that falls from right above your head? The distance it falls isn't what hurts your head. Tell me what's the difference. What's different? Your brain and your skull doesn't care that the penny fell a long distance. If I take a penny on a plane and fly it to Russia and fly it back and then I drop it on my head, the penny doesn't care that it went super far and then hit me in the head. The displacement's not what's important. What's important is the speed. That was a very roundabout way of explaining this, but yeah. What's important is the speed. A penny dropped from right above your head and a penny dropped from a really high distance and having a really great displacement, this penny will be going much faster. This penny will be going much slower, a little tiny velocity right there. So, that means objects falling due to gravity, like pennies, if you ignore air resistance, which you normally do, objects falling due to gravity get faster the farther they fall. If they get faster the farther they fall, that also means they get faster the longer they fall. I said last few videos that cars don't really have constant acceleration. Most things in life don't really have constant acceleration. Gravity is the main example of something that does have constant acceleration. If an object's falling due to gravity and air resistance is negligible, which it is for small, dense objects, it will accelerate constantly. And that acceleration is so often used, they give it a whole new letter. All accelerations are A, but acceleration due to gravity is G, because it's almost always the acceleration we care about in the problem. It's negative or downward 9.81 meters per second squared. It's negative because it's downward. We're going to assume upward is positive and downward is negative, unless I tell you guys otherwise. It's 9.81, which is a nice number. If you have one sig fig, it's just 10 meters per second squared. And G, please don't say G stands for gravity. We've talked about gravity a lot in this class, and not just acceleration due to gravity. G is the acceleration due to gravity. It's on the equation sheet in case you guys forget it, but it's 9.81 meters per second squared. You're all going to have it memorized by the time this class is over. So, it's about 10, which will make this next part really, really easy. If I drop my marker, when I first drop it, this might not seem obvious, but when you drop something, its initial velocity is 0. When you drop it, when I first open my fingers, it's not moving. So it starts out at 0 meters per second. After 1 second, it'll be going 19. When I first drop my marker, it'll be going 0 meters per second. That's when I first drop it at time 0 seconds. After 1 second, it'll be going 9.81 meters per second. After 2 seconds, it'll have the same acceleration for those 2 seconds. So it'll be going 19.62 meters per second. And then it'll go up to 29.43 meters per second. This is constant acceleration. Things that are falling due to Earth's gravity, as long as they're near Earth's surface, like not in space, and there's not that much air resistance, which is true for most solid, heavy objects, they obey the laws we've explained that describe constant acceleration. So that's the main idea for this first lesson. Constant acceleration, the most common example is gravity. Downward or negative 9.81 meters per second squared. The astronaut mentioned Galileo in the video. Yeah, it was Galileo Galilei who first showed this. He dropped two cannonballs, one big and massive, one small and light, off the Leaning Tower of Pisa, and he figured out that they hit the ground at the same time. That was pretty good. So so just for some practice, we're going to look at this. This is an example of what we call a mathematical model. Yeah, we know the Empire State Building is super tall, and we know that if a penny was dropped off, it would be going pretty fast and it would hit your head pretty hard. Does it make sense that the taller a building is, the more time it'll take a penny to reach the ground? Yeah, that's why it goes faster. It hits the ground or your head harder because it was going faster. And it's going faster because it's been accelerating longer, and acceleration is a change in velocity over time. So it has a constant acceleration. If it falls for a longer time, it'll go up from 0 to a higher velocity. There is a mathematical model. If we know the time it takes a penny or any object to fall from rest to the ground next to a building, we can figure out how tall the building is, or vice versa. So let's do that. I'm going to look it up with my brain. Oh, the Empire State Building is 380 meters tall. I'm going to use the guess method, which I hopefully went over yesterday. I didn't record it, and I'm like talking about the future. I'm talking about like time travel. Oh my gosh. So right now it's Sunday, and I'm talking about you're going to see this video on Thursday. Hopefully Wednesday, I taught you guys guess. So here we go, guess. Given we know the displacement was 380 meters, and the acceleration, g, was 9.81 meters per second squared. And I also know that I dropped the penny from rest. So my initial velocity is 0 meters per second. That's all my givens. And my unknown, I'm trying to find the time it takes the penny to reach the ground. So we're going to solve this problem. But one key point, this is negative. Should I make this negative? I could. If I say, oh, the penny accelerates downward and that's negative, that's fine. But in what direction is the penny displaced? The penny is also displaced downward. I'll come back to this tomorrow. You can make D and G both negative or both positive. You'll get the same answer. I'm going to prove it. I'll make them both positive. But in real life, they should both be negative because they're both downward. The penny falls downward due to acceleration downward. It won't matter, as you'll see really soon. E is equation. I happen to know we're going to use D equals V naught T plus 1/2 A T squared. Substitute with units. 380 meters equals 0 meters per second times t plus 1/2 9.81 meters per second squared t squared. Solve with units. T equals, where did my phone go? Ta-da! 8.8 seconds. Good job, me. Thanks. I did it. Thanks, babies, for your moral support. Hopefully I did it right. I'll go check right now. See you guys next lesson.